You tap a pedal and 2 tons of car calm down. Where does the speed go? Into the rotors as heat. Enough from one hard stop to boil a coffee mug of water. That is the whole trick of brakes. They turn motion into heat so fast you never notice. Under your right foot it feels simple. A light push and the car leans forward and slows. You do this 100 times a week without thinking. But nothing disappears. The speed does not vanish. Your brakes grab spinning metal and dump the car's energy as heat in a few seconds. From 60 miles an hour to 0, a typical 1,500 kilogram car must shed about 0.55 megajoules. That is a big number. Picture a kettle coming to a boil. One hard stop has that much energy, and the brakes eat it in moments. Brakes have to solve 2 hard problems at once. First, your leg is not that strong. A small foot force must become a huge clamp on the rotors. Second, that clamp turns speed into a flood of heat. The system must throw that heat away before pads fade or fluid boils. Most of that work lands on the front end. When you slow down hard, weight shifts forward. The front tires carry more load, so the front rotors take more heat. On a panic stop, the split is often around 70% front and 30% rear. So how does a calm push become a serious squeeze? Start with the pedal itself. It acts like a lever. A typical pedal ratio is between 4:1 and 6:1. Push with 300 newtons at your foot, and the push rod can see 1,200 to 1,800 newtons. That push drives a piston in the master cylinder. Fluid does not compress much, so it sends pressure down the lines. The trick is area. If the caliper pistons have 4 to 8 times the area of the master cylinder piston, they multiply the force right at the pads. Under hard braking, modern cars make 1 to 2,000 pounds per square inch in the lines. That is 7 to 14 megapascals. A pressure gauge would spin fast if you could watch it. This is ordinary in passenger cars, not just race machines. There is a boost helping you, too. A vacuum booster uses engine vacuum, or a small pump on turbo cars and electric cars, to add 3 to 5 times your leg force. That is why a calm 30-kilogram push feels like a pro stomp at the calipers. Let's run one clear example, front wheel only. Say the line pressure is 1,500 pounds per square inch. The total piston area in one front caliper is about 2,800 square millimeters. That gives a clamp force of roughly 28 kilonewtons on that rotor face. Now turn clamping into wheel torque. With a pad friction coefficient around 0.4 and an effective radius of 15 centimeters, you get about 3.4 kilonewton meters of brake torque at that one front wheel. Multiply by 2 fronts, and now you see why your seatbelt locks. Here is the catch. The tire sets the final limit. On good dry pavement, the tire-to-road friction can be around 0.9 to 1.0. That caps the deceleration to roughly 0.9 G. Bigger calipers will not help if the tires cannot use it. History gave us this control. 4-wheel hydraulic brakes arrived over a century ago on the Duesenberg Model A in 1921, based on Malcolm Loghead's patent. Drums ruled for decades. Then discs took over with racing proof, like the Jaguar C-Type at Le Mans 1953. Where does the energy go in one stop? Mostly into the front rotors. Take a 7-kilogram rotor. If it absorbs about 70% of that 0.55 megajoules, that is about 0.385 megajoules. Before any cooling, that can raise the rotor by roughly 120 degrees Celsius. Why can a rotor take that? Most street rotors are gray cast iron. It has a specific heat around 0.46 kilojoules per kilogram per degree. Its thermal conductivity sits near 50 watts per meter per degree. It shrugs off repeated 300 to 500 degree cycles without cracking. All that heat must leave fast. Vented rotors hide an elegant trick. Inside the disc are vanes that act like tiny pumps. As the wheel spins, they fling air from the center to the edge. Fresh air comes in, Hot air gets tossed out. At 60 miles an hour, a typical car tire is turning about 14 times each second. That means the rotor vanes are moving a lot of air every second. For street use, good venting matters more than drilled holes. Holes can help clear gas and water, but they can also start cracks. Now to control. Under hard braking, a car wants a front and rear balance close to 70-30. Too much rear pressure and the rear wheels lock first. That makes the car twitchy. So proportioning valves and the brake computer trim rear pressure to keep you stable. Anti-lock braking arrived in the late 1970s on production cars. In 1978, a Mercedes S-Class carried a Bosch system that modulated pressure around 10 to 15 times per second. It does not brake harder. It prevents lock, so you can steer right at peak grip. On loose gravel, a locked wheel can sometimes stop shorter by building a small wedge. Anti-lock chooses control over that odd trick. On real roads with mixed grip and surprise corners, being able to steer while you slow near the limit is the safer bet. Let's talk about life on a mountain pass. Picture a long descent on a highway in Colorado. You slow from 65 to 40 again and again on a grade. At night, when you pull into a turnout, you might see a dull red glow at the rotors. That glow means more than 400 degrees Celsius at the faces. If you ride the brakes, the pads overheat, and the pedal gets long as the fluid approaches its wet boiling point. That is brake fade. Use engine braking and short, firm applications to give the discs time to cool. Electric cars help with gentle slowing. The motor can do regeneration for light deceleration, maybe 0.2 to 0.3 G. But in a panic stop from 60, the friction brakes still take over. Hundreds of kilojoules hit the rotors in a few seconds, no matter what. Fluids matter more than people think. Fresh DOT3 boils around 205 degrees Celsius. DOT4 around 230. DOT 5.1 around 260. But as the fluid absorbs moisture, those numbers drop to the 140s to 180s. That is why fluid changes matter on older cars and track days. And one rule is hard and simple. Do not mix DOT5 silicone with glycol-based fluids like DOT3, 4, or 5.1. The seals in performance are not designed for that blend. Holes look cool, but venting and airflow do the real cooling. Let's zoom back out to the scale of it. A ring of iron the size of a dinner plate eats hundreds of kilojoules in seconds. It swings through 400-degree temperature changes and stays flat enough to avoid vibration. It even pumps its own cooling air as it spins. A good sedan on good tires will stop from 60 in about 110 to 130 feet. Anti-lock keeps you steerable near the limit. It is not magic on deep gravel. The tire still decides how hard you can push the road. Next time you smell hot metal at the bottom of a hill, that is your speed turning into heat and floating away. The rotors did that for you, quietly and on repeat. If you are into clear, oh, that is how it works moments, subscribe and hang out with Buildguts. Drop a like if this helped. There is a whole playlist on engines, power grids, and the hidden machinery under everything. See you in the next one.